Hey everybody, we're going to spend some time going over question number 38 here, which for me is right here. And this one's in brackets, okay, in Brown-Lemay and Burst. And the reason why it's in brackets is because I think that there's a lot going on here. So we're actually only going to do part A of this one. And I would recommend, again, with any of these problems that stop the video, pause it, see if you can come up with an answer, go through the response and see if you see where you're getting caught up. Okay. Now, this is different than some of the other ones that we've seen because if we look, we do have a concentration where iodine is held constant, but this disulfate ion, there is no concentration where there's no experiments where the concentration of peroxydisulfate is actually held constant. This shouldn't be a problem, okay? But I wanted to go through one of these for you just so you can see how it works. Now, you shouldn't have any sort of issue with this because you can always revert back to the rate law in order to solve a problem like this. Okay, so let's take a look. So what I've done is I've copied the data over here. This is question number 38. Okay, and so we want to know what the rate law is. So the rate law, R equals K, and I use the script K because I don't want to get confused with capital K. That's the equilibrium constant. So that's K, the rate constant, times the concentration of S2O8 2 minus to some power m times I minus raised to some power n. Now this is kind of an interesting reaction because this reaction is done in the lab all the time. This is what we call a clock reaction. What it'll do is it will change colors. It'll go from black to white, or to colorless to black to colorless to black to colorless to black to colorless. And so you can measure the time that it takes to do that, and then you can figure out the rate. So it's kind of interesting. But we can also from that figure out the initial concentrations because we are setting that reaction up. So it's kind of a popular experiment to do in the lab. Okay, so how are we going to solve this? Well, we're going to compare experiments 1 and 2. Okay, we are going to do that because these two are held constant. Okay, these two are the same, so they're going to cancel out. So we're going to compare R2 to R1, which we always kind of take the bigger one and put that one on the top. So this one's the bigger one. So 3.9 times 10 to the minus 6 over 2.6 times 10 to the minus 6. And that equals K times the concentration of S2O8 2 minus raised to some power m times I minus raised to some power n. But it's R2, so this is all the 2's, over R1, K S2O8 2 minus to the power m times the iodide ion to the power of n. Now, K is constant no matter what. So we don't have to worry about that. The only time K is not constant is when the temperature changes. And I've never seen a problem in this sort of chemistry class where the temperature changes and we have a new K and we have to do something with it. So that's fine. And now if we look, iodine is the same in experiment 2 and experiment 1. So this also cancels out. Okay. So we get that equals, whoops, let me go back to this color. So that equals, okay, 0.027 over 0.018, and because these are the same power, we can just group them together and raise it to that whatever power that is. We only have to do one. Okay, so hopefully you see a little pattern here with the numbers, but I'll do it anyways. Okay, so I'll do the math anyways. 3.9 times 10 to the minus 6 divided by 2.6 times 10 to the minus 6. Okay, and so that is 1.5, and then 0.027 divided by 0.018 is equal to 1.5 raised to the m power. So that means that m equals 1. Okay? Now, the dilemma is that how do we figure out what n is for, what the order is for I? Because none of these are held constant. So if none of these are held constant, how does it cancel out? Well, let me just tell you that you don't have to have one where it's held constant. Okay? Now, once you find one, you can find the other one by reverting back to the original thing. Okay? Reverting back to this whole thing written out. Okay? So what I'm going to do is, because I have a math trick in my head, what I'm going to do is I'm going to compare experiment 2 to experiment 4. Okay? I'm going to do that because these two are twice that. Okay? Are twice. Okay? So I'm going to compare these two things. So we're going to take the bigger rate, which is this one. Be careful of the power. That's a -5 power, and that's a -6. Okay, so we're going to do rate 4 over rate 2. So it's rate 4 over rate 2. And rate 4 over rate 2, let's see, rate 4 is 1.4 times 10 to the minus 5 over 3.9 times 10 to the minus 6. And that equals K times the concentration of S2O8, 2 minus, raised to some power M, okay, times I minus, but we know what we know what this power is. M is equal to 1. We are trying to find n here, right, because we just solved for n. All of that over experiment 2, S2O8, 2 minus, raised to the first power times I minus raised to the n power. Now, the thing is here is that we don't have, we can't cancel any of these out. The only thing that we can cancel out really is the the rate constant. Okay? But that still gets us to the answer because we have everything except for one unknown. And one of the tricks I always remembered from algebra is that for as many unknowns you have to have that many unique equations. So we only have one unknown, so we have one equation. So we can do this. Okay? So let's do this. Okay, let me bring up my calculator. Okay, maybe where should I put it? Down here? Okay, so I'll bring up the calculator. And so let's do 1.4 times 10 to the minus 5 divided by 3.9 times 10 to the minus 6. And so that is equal to this weird fraction, or this weird number, 3.5897, whatever. Okay, but that equals, what's the concentration of S2O8 2 minus in experiment 4? Well, it's 0.05. So let's see here. 0.050 raised to the first power times iodine. Iodine is 0.072. 0.072 raised to the n power. That all over now for experiment 2. So the rate of 2, let's see, so this is not the rate of 2, the concentration is 0.027 raised to the first times 0, and let me just double check that I minus is 0.36, but that's why I picked it, 0.036 raised to the n. Okay. So now, let me just take this and move this kind of away from the calculator here. Okay, so now we're going to just, I say just, but we're going to solve this. Okay, we're going to solve this for n. Okay, well, 0.050 divided by 0.027. Okay, so this equals 1.851 repeating times, what's this? 0.072 divided by 0.036, but I know that that's 2, so that's going to be times 2 to the n. So now we're going to take that and we're going to do some division. So 3.5897 divided by 1.851. Okay, and that equals, let's see, 1.939 equals 2 to the n. Now, this is where you have to be okay with math, is that we're going to say that is just about 2 equals 2 to the n. So n is equal to 1. Okay, so nothing canceled out, but we were still able to figure out the n. Now the question wasn't to figure out what the orders were, but the question was to write the rate law. So the rate law, to finish off the question, is R equals K times the concentration of S2O82 minus to the first times the concentration of I minus to the first. Okay, so that, I hope, shows you how to calculate the rate law without having one of the reactants cancel out. Okay, so that was question number 38. That was question number 38. Okay, great.